Oh, yeah, that's it. This is a picture taken by Tom with his cell phone, I understand. And up here, there is either a defect in his camera or more likely it shows a star. If you remember the 2017 eclipse, there was within that range of the sun during the eclipse, you could see the star Regulus. And it was about the same brightness. Now, we did a lot of talking on the SBAU Astro Hour about the comet 2P Brooks or Pons Brooks being within the field of view or close to this, and it was, but it was way too faint to show up. Nobody's going to have a photograph of that during the eclipse. But it was a good event. If you came out to the marketplace, you could see the sun through our hydrogen alpha scopes, and it showed characteristic prominences that you would only see if you were somewhere where it was total. But it wasn't here. It was about 50 to 55% for us. But you could see the prominences out there. There's one characteristic one that looks like a capital lambda. And that's the signature, the spotting feature of that eclipse. The internet, especially Facebook, is covered with fake solar eclipse pictures. A lot of them obviously faked, but if they don't have that little lambda in there, it wasn't this eclipse.
That was red point that was in the diamond ring?
No, that was, we didn't see a diamond ring here.
No, but I did at Fort Worth.
Oh, okay. What you would see when you're at Fort Worth, before, depending on which diamond ring you saw, because you get one at the very beginning of the totality and one at the end.
And it was a really red spot.
No, that's just the sun coming up rising over the mountains on the moon.
No. Jerry,
But
she's talking about the red thing with the prom.
I know, but she's pinning it to the diamond ring.
Yeah.
And before the diamond ring, when the diamond ring didn't happen and wasn't there, that's when you see the prominence. So maybe it was the thing because it was red. But we got to see it here without having to pay the travel fees.
Or in the Texas barbecue.
Yeah, okay. Okay, John, we can go to the program for tonight. All right, thank you. So we have a very interesting speaker. I'm looking forward to that tonight, which will be introduced shortly by our vice president. But first, we're going to go through our commercial with the merch manager. Try to monetize things.
Okay, so I'm gonna try and hold this and also show you some merch. Oh, thank you, sir. Okay, perfect. My name is Pat McPartland. I'm the merch manager and also the 2024 treasurer. So I can not only show you or sell you merch, I can take your money. And if you want to join tonight, then Andy Allen and I can help you with that. Andy is way in the back, raising his hand. He's the secretary for this year. And I have all kinds of goodies, and I'm back at the table back over there in the corner. This is our beautiful tote bag. It has the colorful logo and has a pocket in front and a zipper pocket. And if you travel with airline, and I'm checking this on the airplane, it's so convenient, and I love it. That's why I sell it too. But we also have mugs and we also have patches and that sort of thing too. So come on back and take a look at what we have. And I welcome you all tonight. Thank you for coming.
Should we be scrolling through these view rooms as we?
Yeah, hit the arrow keys, Jerry. And you can see what Slack runs. We just finished merch, so keep going.
Okay.
Hit the arrow again. And then the next one.
Yeah.
There you go.
Okay, and next on the venue is, the menu here is the events calendar.
Okay, thanks, Jerry. Okay, we still have a couple of events left for April. We're usually earlier in the month when we do this, but coming up on Monday evening, weather permitting, we got telescopes out at Encino Royale for the folks living out there. Set up at about 6:30 in that neighborhood. And then on the 18th, on Thursday, Vieja Valley has their science night. I don't know quite why they call it a night because it ends at 7:30 and the sun doesn't set until after that. But if you've got a scope that'll do solar or you just want to talk astronomy, you can show up there. That's from 5:30 to 7:30. And they offer dinner to volunteers. And then on Friday night, third Friday of every month, is Westmont College at their observatory from 7 to 10. And then what else do we have? Then we have the big event. Okay, on Friday the 26th is Kaleidoscope, which is sometimes up to 2,500 Girl Scouts at Live Oak Campground. Yeah, Edgar calls it, it's like Custer's Last Stand. Oh, there's Edgar, yeah. And but to go to that, you have to get a background check, not only our background check, but the Girl Scout background check. So if you're interested in that, you haven't already contacted me, let me know, and we'll try to get you in before that time. And we usually survive it. Bruce almost didn't, but he's back. So that's it. Thanks. Oh, and coming up next month is Astronomy Day. So watch out for that. All right. Thank you. International Astronomy Day. That's where we set up out at Community Rail Marketplace and spend the whole day there, basically, and have a star party in the evening.
Why don't you mention our potluck? We might get some new members coming to that.
Well, that's in July. Yeah, July 5th. We'll have a potluck here instead of our meeting. So if you like food, that's an excuse to come out here. Okay, thanks, Jerry.
Thank you, Chuck. Yeah. Okay, this is Ron is on,
You're kidding.
our illustrious vice president.
Doggone it. He's still alive?
This is really outreach too. Yeah.
There's that man we're gonna have talk to us. Thank you, Mr. President. Jerry Wilson, everybody. Let's hear a big one for him. Somehow the people are watching us at home, the ones that don't make it here. We're somehow sending this out on Zoom. And the race for intelligent life in the universe, since there's very little of it here on this planet, it's coming up. But I got a few things I want to do first of all. We like to know who's here. So there's three parts to this. You members don't raise your hand, but everybody who's coming here for the first time, anybody new, brand new, raise your hand. All right, keep your hands up. You folks that are members and have been here before, these are the ones you're going to want to take to lunch and wine them and dine them, buy them a beer. You don't have to join, but we'd love to get one. There you go. Who's been here before but is not a member, just out of curiosity? All right, okay, well, you guys are honoraries. That's nice. Okay, I wanted to just quickly introduce, since the rest of you that are members, all the members of SBAU, Santa Barbara Astronomical, look at that. Let's give yourselves a hand. I want to quickly introduce you. Since a month ago, we had on screen in Fleischman Auditorium, Bob Berman, the many years world-renowned columnist for Astronomy magazine, who announced from his home in upstate New York during that time that he had stepped down. He was still doing a lot of other things, but he did it for us, for a song. And I now have, believe it or not, Astronomy magazine's new issue with a cover story called Music in the Cosmos, or Music of the Cosmos. It was written by an old friend of mine I used to interview 10 years ago when I was on the radio, and we had the symphony as our regular sponsor. And I get to have Near Cabaretti, the maestro, in my studio once a month. And this man publicized and was hired to publicize all the symphony programs once a month. He's now a member of the club, and his name is David Grossman, and he wrote this article. Dave, would you stand up? I'm gonna let this gentleman peruse this and hold it for me while I get rid of a couple of other things. Thank you for coming, all of you, and thanks for joining, Dave. It's good to see you again. He's gonna try to help me get Alex Filipenko. I've been told he started here in 1970, believe it or not. He was a young man like we all were back then. And UCSB was in the club. And they said, you'll never get him because he refuses to come down. And I thought, well, this was before Zoom. So next year, we're going to have our 70th anniversary. 1955, which started on, I think, at City College on the campus. Later on, about 10 years later, it merged with another. That's not right. None of that's right.
55 was called the Santa Barbara Star Cluster. And
Right.
it was Captain Crutchfield Adair that started.
And it merged later with another club, right? It never merged?
It became the Santa Barbara Astronomy Club, and they finally merged with the Astronomical Unit in 1999 or 2000.
Well, if they merged with Astronomical Unit was alive, and that was us
No.
later than 50.
The Astronomical Unit started at City College in like 1982 or 1985, somewhere in there.
I got you. Okay, well, I'm working on possibly with the help of Dave, who's going to help me, he says, getting Alex to maybe at least greet us online if he doesn't come to town, and maybe we'll talk to Randy Rouse, the mayor, about it, declaring an official year of astronomy. Here's my deal about astronomy, as I've said to you before, of all the sciences, it's the one that almost gets the most news. Certainly Monday was a good example of that. It was almost a national holiday. But every week, sometimes every day, there's a new rock coming that's going to miss the Earth or a new launch. You know, the geologists don't get much time on the air, do they? How many times do paleontologists dig up dinosaur bones and make the news? But what is the science that gets a lot more than ours in news? Medicine, pandemics, vaccinations, boys and girls. But ours is the fun version. And Monday was a good example of that with our 2/5 of the sun covered up. Anyway, next month, May 3rd, Dr. Larry Martinez will be here in one of our 3 venues. I like this little room. It's kind of nice. Normally, as you probably well know, we meet at Farrand Hall, which is the smaller of the little venues down here next to the Gladwin Planetarium, or the big place, Fleischman. So you have no idea, John, where we're going to be next month?
As far as I know, it's either here or Fleischman.
The big one. All right, well, we're going to close the doors this time, so it'll be warm all the way to the floor, not just from the stage up. Okay. Incidentally, Jerry just touched on it. We just started our 4th year and have not missed a Monday except this week of our weekly vlog called the Santa Barbara Astronomical Unit. We put it down to SBAU Astro Hour. It's on YouTube. You can remember SBAU Astro Hour. I don't think .com. No, that's emails. We're always there, and we start with cartoons. And the man has been sending us cartoons like you wouldn't believe. We got enough for 3 weeks as we reconvene on the screen Monday morning at 11 a.m. to talk probably mostly about eclipse and about what our guest speaker is going to be talking about from the Inland Empire, brought his wife. And speaking of the old days, let me tell you about this guy, Dr. David Kary, Citrus College, grew up in New Westminster, British Columbia, Canada. And in 3rd grade, he learned about the solar system, as most of us did. Started by attending the University of BC, British Columbia, earned his Bachelor of Science in Astronomy and Geophysics, doing research on Jupiter and the 4 Galilean moons. He got his PhD in astrophysics at State University of New York, moved to Santa Barbara back in the 90s, and researched and taught at UCSB. Spent 2 years here at this very museum. So afterwards, if you got time, you might want to ask him about that. He met his wife, who's sitting next to him in the front row, The lovely Joanne Eisberg became Joanne Kary, Kary. She was an astronomy historian, now retiring from Chaffey College, Chaffey Community College. That's down in her area. They have a daughter named Annie, and they moved the family to the San Gabriel Valley back in 1999. But he loves us and our planetarium and our club, and we're going to have the missus speak to us hopefully later in the year. Fascinating couple. Don't get many husband-wife combos, but get ready for a life of intelligence in the universe from Dr. David Kary, ladies and gentlemen. Citrus College. Did you say it's great sound? Okay.
So, and we just want to share screen. And then we want to do this one, share. And what's that, sir?
All right, thanks very much. Let's see. Yeah, okay, good. We got that. It is so nice to be back here with the AU. I first got to know this club back in 1996 when I started working here. The president was a guy named Bob Brown. I don't know whatever happened to him. But no, I've really always enjoyed my time working with the AU. I've always thought this is one of the best astronomy clubs I've ever had the pleasure of working with. I've gotten to work with many different places. But this group has such a wonderful commitment to outreach, to education, and just such a neat group of people who get together here. And that I've always really appreciated that. So I think, give yourselves another hand because you really do. It's really quite something. So what I want to talk about today is it's a really big topic, and I'm sure many of you have thought about, heard talks about, read about different parts of this story. What I hope is maybe a little bit different here is the way I'm going to approach this is I'm trying to put together a whole bunch of different pieces at once because I think now we can. For once, we can start talking about the search for life in the universe in a much more comprehensive way than what we usually get, especially just an hour's talk. It's not just something where you're looking at one little piece or one other little piece now. I think we can meaningfully think about it as a search that involves many different parts, that involves a lot of different branches of astronomy. And I think we can think of it as a race. And hopefully I can convince you that that's kind of where we're at now. So let's see here. There we go. Okay, so here's the basic outline of what I want to talk about today. I'm going to say a little bit about kind of the history of, and maybe more, the history of our attitudes towards the search for life in the universe, because it's changed, and it's changed a lot in my career. Really, I've seen it, go. It's so different now from what it was back when I was a student. Then I'm going to talk a little bit about life and kind of the ways we might categorize life. I'm going to do that really fast because that's a topic you can really get lost in a hurry. And so I don't want to do too far there. But then I really want to spend the bulk of the time talking about 4 different ways that we can go about searching for life in the universe. And this really kind of covers the gamut of how it's being done or how it could be done these days. And then we'll wrap it up with some final thoughts about where we are in this process. But let's dive right in here. Whoops, let's hit that one. Good. Okay, so searching for life in the universe. As I said, this is an idea that has our approach to it has really changed.
in my lifetime. So, you know, it's something that, of course, we've been the public in general has been very interested in for at least 150 years now. Honestly, going, you know, well into back into the you know, late 19th century, you know, with some of the early speculation about Mars, and that really was generating a lot of interest in the public. Among the scientific community, though, this is something that has really waxed and waned, use a good astronomical term there. It's, you know, there have been times when it's, you know, been taken very seriously. There have been times when you really didn't want to do that. Certainly when I was a graduate student in the late 1980s, early 1990s, unless your name was Sagan, if you were interested in this, you didn't talk about it. Honestly, it was a career killer. You know, nobody took it very seriously. Very few. There was, you know, a handful of people in a few places, but mostly no. You know, if you were a graduate student, you told your advisor, "This is a really interesting topic." They'd say, "You don't want to do that. You want to get a job. You don't want to be talking about that kind of stuff." And that was very much. That has changed 180 degrees. And I want to just say a few words about what caused that to change. I'll say a lot of it happened when in the period when I was actually here at the museum. And just a couple of years around that is when that really started to change a lot. In particular, there was this little rock. I actually remember when I was here really giving a talk about this rock. It is called ALH 84001, and it is a meteorite. And it was discovered in 1984. That's where the 84 comes from. It's in Antarctica. Some years later, it was recognized that it wasn't just any old meteorite. It actually came from the planet Mars. So it was something where something had smashed into Mars and threw a bunch of pieces out into space, and this was one of the pieces of Mars that got thrown into space from it. But in 1996, something really spectacular happened with this thing. And that is that a group of quite respectable scientists, I mean, these were like your top people in the field, looking at this meteorite, studying it, you know, taking pieces, analyzing them in detail, published a paper that said they thought there was evidence that there had been life in this rock. That they were seeing both chemical and physical evidence in here that showed that they said pointed to at some point there was something alive in this thing. And not while it was on the Earth, but back when it formed on the surface of Mars. That was huge. I mean, that was a major piece of news. I mean, this is like the president of the United States actually had to give a statement about this. It was that kind of story. And it really shook up the scientific community. Now, I'll say in the years since then, that finding itself has been sort of pushed back on quite a bit. And, you know, I think the best you can say is, yeah, there's probably other ways you could get the pieces of evidence they saw there. So it is no longer considered as, yes, this is that clear sign that there was life. No, it isn't. But it really sparked an interest at that point and really suggested that, hey, this might be something serious we should look at. Another thing that happened around the same time was the first discovery of exoplanets. And so, you know, this was started with a system called 51 PEG. And then, you know, if anybody who was around then remembers that, it was, you would get one And then, a few months later, another one or two would get announced. And slowly over the next several years, they were finding one after another. And there was a trickle of these things came in. And then in 2009, the Kepler mission was launched. Kepler was a spacecraft that was in Earth orbit, but studying, specifically looking for exoplanets. And it was finding them. And it was amazing because they were just finding one or two or three. They were posting, yeah, we got another 1,000. And this, suddenly we had, the study of planets around other stars could explode. We could suddenly start talking about these things, not just as individual interesting objects. We could do statistics on these things. We could start meaningfully talk about, so how many of them are out there? Where are they? What types of planets are they? For the first time, we could really, talk about the population of planets in our galaxy. And the key conclusion, the sort of most important one, is that exoplanets are incredibly common. They are normal. When you look up at the night sky, just about every star you see has planets going around. And for folks who grew up before that era, that's amazing. That's wow. We wondered if any of those stars had planets. Now we know they all do. And that's a whole different attitude. That's suddenly and there are planets that are the right size, we think, and the right distances from their stars that, you can now start thinking, yes, if you want to look for life, well, now that we got the places to look, that's now a real thing. And that's a whole different view. And so this was another one of those things that really started changing our attitudes towards this. Another discovery, this one much more recent. These are two really. One I 2017 Yuan Uamuamua. I'm better at saying that. I don't know how to have it. And then two I Borsa. These two objects were both hyperbolic objects. That is, they are from outside of our solar system. They came in clearly moving much faster than any solar system object. That's why we know they could not have been originated as part of our planetary system. They came in, they flew through, they got close to the sun, they whipped on out again, and bye, they're gone. They're not coming back. So these were interstellar objects that were formed in some other part of the galaxy. We don't know where. Came in, flew through, and went out again. And this did a few things. First of all, it illustrated to us, we really are connected to all this stuff out there. That's not, we can't just treat ourselves in isolation, right? And it also was kind of a test of whether or not we could detect something from outside of the solar system coming through. I remember when I was a grad student asking that question, and my advisor said, "Well, do the calculation. What do you think? Is there any chance we should have seen something if they were coming through?" So I threw some kind of back of the envelope calculations. I'm sure hundreds of other astronomy grad students did the same thing at one point or another. And came up with the numbers of, maybe there's a chance we might have seen one, and that wasn't clear. These ones, it was dead on. Okay, and they really really sort of showed us that we could see something. If it came from outside of our solar system, we would see it, especially if it came into the inner solar system around the side. I'll come back to these here a little later on. There's one other key discovery that was made in this period. It's a little different type of discovery. It happened at NASA, and it was NASA discovered that there is a direct connection between aliens and the color green. And of course, I mean as in money. I mentioned ALH 84001. When that meteorite was announced as being potentially having evidence for life, at that time, NASA was in a hiring freeze. They couldn't hire anybody, agency-wide. Okay, because the budget was really tight. They just couldn't, they said, no, we can't hire anybody else right now. A month after that discovery, that hiring freeze was broken. And I know because the guy I used to work for, my thesis advisor, got hired at NASA Ames because he was working on origins of solar systems. And this happened. NASA suddenly happened because NASA suddenly realized, hey, we're getting interest from the political side. That's freeing up money that we weren't seeing before. There's a real interest in this out in the public. And so now you go to the NASA website and there you go. They have an astrobiology page at the NASA, on the NASA. This is a central part of the NASA mission. This looking for life, looking for places life could be, looking for habitability. They learned their lesson. They know this sells, and they're definitely, they've learned to take advantage of that. And so, with that in mind, and NASA is one of the major funding that other agencies that funds astronomy research also recognize this. So it is now true that if you're interested in looking for life elsewhere in the universe, there is a lot, the resources are out there now to support that. It's no longer a career killer, it's now a career advancer. That's why I think we now have the race now on. We still have the basic question. We still don't know if there is life out there. Okay, that's still like that core question still exists. But if it does, we can now meaningfully ask, where will we find it first? And how will we find it? And that's really what I want to talk about here. What are those wheres and hows, and how do they compare as we look across it? Now, I should say, I'm going to be moving pretty fast through these. Almost every slide in this talk could be a full hour-long talk all by itself. So, I'm going to be skipping a lot of the details and just kind of hitting the high points here. So bear with me, and maybe afterwards, when we want to talk in a little more detail on some of those, we could. But let's take a look, first of all, what do we mean when we talk about looking for life? And really, searches for life tend to divide into two major approaches in terms of the type of life they're looking for. One type of search is really looking for just any life, okay? Anything you could call alive. That's all they're looking for, anything at all. Now, you can get into some really interesting philosophical discussions in trying to define, well, what is alive? And I don't want to do that. Because that by itself, like I said, that's a whole big long talk by itself. Probably still don't get a resolution. But there's some kind of broad agreements on some of the components of this, and they let you define some of the things you would need to be looking for. And usually those involve certainly an energy source. Okay, there has to be usable energy for living organisms in order for them to do anything that we call living. There has to be the raw materials that you need to make that living organism. And usually we tend to think of that as something carbon-based. Carbon turns out to be really good at making big, complicated molecules, which is kind of what you need if you want something that's actually going to start, say, making copies of itself. Okay, that's not going to be something that's going to be simple as a water molecule. So you need something a little more going on than that. And you need an environment where all that chemistry can happen. And on Earth, at least, that environment is water. And so water tends to be what we think of, but I will mention at least one exception here as we go along. But that's, tends to be what we think of. Now, when I say any life, I really mean any life, anything at all. It doesn't have to be like, giant insects or sandworms or anything like that. I mean, bacteria, okay? Plankton would be amazing. Any kind of life at all. And when you look at the history of the Earth, most of our history, this planet has been dominated by single-celled organisms. So that's, you frequently, when you talk about looking for economic, that's really what they're talking. You got a planet with lots of plankton. That would absolutely do the job. Don't underestimate single-cell organisms because they can have global effects. They can completely change a planet. And so that's the kind of thing you need to look for. Single-cell organisms really reshape the surface of the Earth. And a lot of the key things that would make the Earth observable as a home of life is a direct result of single-cell organisms. So that's really key. And that brings up a term I want to introduce here, what we call a biosignature. And so I'll throw this word around a lot. And it's really just anything that we see in the data, any kind of signal that we think, it could be a spectrum, it could be a color, it could be some other effect that we see in observing a planet that we think could only be produced by living organisms. And I'll get to some examples as we go along. But that's when I say biosignature, that's what I mean. Something that we can measure that we think requires life. Okay, so that's one type of search. The other type of life we often look for is a much more limited type, what we like to call intelligent life. And that, of course, again, intelligent is a tricky thing that you can to define. And so in a real practical sense, what we really mean by that is technology using. And in fact, again, it's got to be a kind of technology that has an impact on the planet, at least. And one of the criticisms of searches for intelligent life for many years was that since all they were really looking for were radio signals, that what they were really looking for, in fact, were exo-electrical engineers. Okay, that's really limiting your pool pretty seriously. So you probably don't, you want to see if you can broaden that some. And we'll talk about some of that as we go along. But that is a thing we need to keep in mind. For most of the history of the human race, we would not have been observable by any of these techniques. Now, maybe we'll last for another, several million years, and that won't be true over the whole history of the species. We don't know. But certainly right now, we need to remember this is one where we're going to miss a lot of intelligent species if they're out there. Unless they are doing certain very specific things that we can detect. All right, but there certainly are technologies that can have global impacts. And that's what we really want to be looking for. Okay, and maybe even beyond the globe. We'll give a couple of examples of those as we go too. So there's an equivalent to the biosignature term, and that's what we call a technosignature. And a technosignature is simply, again, something we can measure in our data when we look at a planet or star or whatever, that that we think could only have been produced by some form of technology. It could not have simply happened naturally. So we'll talk about some technical signatures that we can look for as well. Okay, so let's start our sort of survey of the ways we look for life within our own solar system. And I want to talk about and start with the broad category, any kind of life, right? And especially in our own solar system, that's kind of this, mostly that's kind of what we're stuck with, right? Because we've now seen the planets in our solar system. There don't appear to be any cities out there. There don't appear to be any advanced technologies kicking around our solar system except ours. So that's where we're stuck. But this also has the longest history. Okay, we've been looking for evidence of life in our solar system, again, for easily 150 years. By telescope from all that time, more recently by spacecraft, and even more recently in situ, actually getting down on the surface of worlds and digging up pieces and seeing what we can find. We also do have meteorites. You have, as I mentioned, occasionally things get knocked off of some of these worlds and find their way to us. So that's another way we can get samples to look at to see if there's evidence for life. So the philosophy here, the thing that has guided most of our looking for life in our solar system has been follow the water. That's really, we look for places where there either is liquid water now, or there might have been liquid water in the past. And that will definitely drives the choices that folks have made in terms of where to look. This is a major focus at NASA. I mean, that's you throw that phrase "follow the water" at NASA, and they know exactly what you mean. Okay, that's a term they use a lot in their astrobiology. But there's another kind of broader philosophical point that I want to make about looking for life in our own solar system. If the only example we have is the Earth, there's always the question, well, maybe that means that maybe the Earth is just like this 1 in 100 billion shot that happened to come out, everything just happened to come out just right, and life formed here. And maybe there isn't anything, maybe we're the only ones in the galaxy. But if it happened twice, just in our solar system, then that argument falls apart completely. At that point, you got to expect that the galaxy is crawling stuff, right? It's got to be everywhere. If you get it twice in one solar system, then you look at the 100 billion solar systems in the galaxy, and you say, yeah, there's all over. So that's a thing that underlies a lot of this search for life in our own solar system. Okay, let's talk about a couple of the places that we like. Mars, of course, is the sort of perennial favorite, right? We've been looking at Mars for, 150 years and thinking we've been seeing evidence for life. Sometimes we've been fooling ourselves pretty effectively about that. But there are still some reasons to take seriously the ideas of life on Mars. And certainly it is a key focus of our Mars exploration. You look at the mission statements for all of these spacecraft: Viking, Spirit, Opportunity, Phoenix, Curiosity, Perseverance. They are all have in there either looking specifically for life or looking for evidence of habitability, looking for whether or not the right conditions exist. So yeah, this is very much part of there is no planet in the solar system besides the Earth that has had nearly as many spacecraft studying it as this. And looking for evidence of life has been one of the key drivers throughout that process. So the underlying assumption here nowadays is that Mars was once a much more habitable place than it is now. Right now, it's a nasty place. You wouldn't want to live there. Okay, it's pretty harsh. But if you were looking at Mars, say about 3.5 billion years ago, around the time life was really getting going here on the Earth, it's a very different place. And it looked a lot more promising then than now. So most of the work that's looking for life on Mars is much more focused on evidence of, especially the chemical evidence for habitable environment, for signs of biological processes that would have happened billions of years ago. And not nearly so much today, because it just doesn't, it's really hard to do it today. Also, of course, there's always the idea of looking for fossils. Now, that's not one you'll find in most of the official mission statements that you see. But if you actually talk to the Mars scientists who are doing the research, especially if you see them at the end of the day at a conference, so ask them what are the kind of things they'd love to see. I mean, absolutely, they'll say, yeah, if we could see something that looked like a fossil. And they would, that's going to be on the short list of samples we would love to get back to Earth when we finally do a sample return mission in a few years. So that's always there. And that's certainly something that people would like to find. So the promise here, why Mars? Well, Mars in the past had one of the most Earth-like, if not the most Earth-like environment in the solar system. Okay, it looked, you could see a lot of things on there that were, we could see there were clearly rivers, there were, lakes, there stuff was going on there that would be really promising for life. It also is, one thing that separates it from the Earth is that it doesn't hide its past the way the Earth does. Okay, the Earth is really good at getting rid of all the evidence of what happened in the past. There's stuff eroding away, getting covered, and it's really hard to see what went on in the past. Mars hasn't been doing that nearly as much. And so there's a lot of, you can still find big chunks of the Martian surface that have been sitting there, except for the occasional asteroid impact, for billions of years. And that makes it so we can really get to the history of Mars much more easily than we could with a really active planet like the Earth is. The challenge, well, it is a really nasty environment. Like I said, you wouldn't want to be there today. It's chemically and temperature and for a whole bunch of other reasons really harsh for life. And one of the big debates going on in the community is, in the past, yes, we know there was water on the surface of Mars, but for how long? How much of it was there really long periods, large bodies of water that were there for long enough that really interesting chemistry could start happening? Or was it just kind of like a really short period where flash flood rolls through and then it all evaporates and freezes and it's gone? And there are certainly a lot of Mars scientists who think that the second story is what actually happened. That it was not very stable, that it shifted between warmer, wetter periods and cold, really dry periods. It was bouncing back and forth, and it may not have had that kind of long-term stability you would think you would need to really get life going. There are folks in the Mars science community who are actually on both sides of this debate. They know this, they all know this stuff, they're all smart people, and they're looking at the same data and they're really just interpreting it in different ways, which tells you there's still a lot of uncertainty. But that's kind of where we are with this right now. Okay, ocean. This is a term used generally for any world that has lots of water in it, but it is most often used to talk about some of the moons of the outer solar system that have lots of liquid water below a layer of ice surface. So when we look at the surface of these moons of the giant planets, Jupiter, Saturn especially, we see the icy surface, but we know below that there's an ocean. And these can be really big oceans in many cases. A few of the examples include Europa, which is a moon of Jupiter, Enceladus, and Titan, both of which are moons of Saturn. And yes, I'm going to come back to Titan because it also has some other stuff going on, but it does have a liquid water ocean below the crust. It's quite a ways down there, but it is under there. These, if you wanted to pick where are the places in our system right now that look best for finding life today, these are really the ones. They have the water. We're pretty sure they've got the organics. There's so much organic stuff in the outer solar system. That should not be a problem at all. And they have the energy sources. So they look good. So that raises the assumption, at least, that many people like to make here is that if you've got the right conditions for life, then it should be there. Okay, it should have gotten started. And we don't know that, but that is certainly a working assumption a lot of folks who are studying these worlds are making right now, and really trying to test with their exploration. And there certainly are plans to start testing these ideas. There is a spacecraft that's being developed right now called the Clipper that will go to Europa and try to and get a better handle on what that world is like. There are others that are in the works or further on to get out to the Saturn system. And the promise this gives us is huge. Okay, if there is life on these worlds, the possibilities for life in the universe open up so much. If suddenly you're not just stuck on terrestrial planets in a little narrow band around their star, but instead they could be on Jovian moons. Suddenly the number of places in the universe where you could have life explodes. You get 10, 100 times as many places where you could be looking for life then. Life then becomes really, really possible. But there's some challenges here. These are really low energy environments. Okay, you're a long way from the sun. So Jupiter is 5 times as far away from the sun as the Earth, which means it gets 1/25 as much sunlight. And on Earth, sunlight is like the big driver for life. Now, yes, you could use other kinds, use internal heat, geothermal type energy sources as well, but they're not going to give you nearly as much energy to work with as what life here on the Earth is used to as far as life. So that makes it hard, not possible, but it definitely makes it a challenge. The other thing is more just an exploration problem. If it's all happening under a thick layer of ice, and I mean, even the thin layer of ice like Europa has, that's still 10 kilometers thick. Some of them, Titan's ice layer, we're talking more like 100 kilometers. That's going to be really hard to explore. Now, there is one possible workaround for that, and that is Enceladus. Enceladus is a little moon of Saturn that does have an ocean under its ice layer, and it has geysers. You can see those in this Cassini image of the blasting up. In fact, Saturn, one of Saturn's rings, what's called the E ring, is actually ice crystals blown off of this moon and that are now orbiting around Saturn. So maybe we could sample the Enceladus ocean by flying a spacecraft through one of those. We've actually done this once, but it was the Cassini spacecraft. It wasn't built to look for this kind of thing. So they flew through it and they made some measurements, but they could not really tell you much about what the composition of this, or whether there was any interesting organics in those geysers. But there certainly are folks who are working on coming up with a mission that would fly through those geysers, and to specifically with the purpose of sampling what's in them and seeing if we can do the chemistry on those oceans. Okay, what about Titan? I throw in this one. Titan is the second largest moon in the solar system. It's a moon of Saturn. I mentioned it's got oceans under its surface, but it also has something real neat going on. It's the only world besides the Earth that actually has a liquid on the surface where you could actually see it. It forms lakes, possibly rivers. The only problem is the liquid is water. It's liquid methane. Basically, it's liquid natural gas. Okay, it's 93 Kelvin here. That's like a couple of 100 degrees below zero. It's really cold. So water is actually the rocks on the ground here. That's water. Water is a solid, and it's going to stay that way at the surface there. But this raises some really interesting ideas. I'll also say that the atmosphere of Titan is also really interesting. There's some, the atmospheric chemists have really been scratching their heads about this. In particular, there's a lot of methane in the atmosphere of Titan. And that's a problem because methane isn't supposed to last. Methane is supposed to disappear. Okay, it's a pretty reactive chemical, kind of like oxygen in our atmosphere. It's not supposed to stick around, but it does. And that's making people wonder you gotta have something making that methane. And yes, it might be volcanic, or maybe there's something exhaling it. That's one of the things that's being thrown around out there. So that's kind of what prompts a lot of the interest in this. So here's the assumption you have to operate under if you want to look for life on the surface of Titan. That you can have life that is not based on water, but instead on some kind of organic solvent like ethane. And so that's and there absolutely are people who are trying to figure out whether or not you could make that work from a biochemical standpoint. So there are certainly missions that are in the works to try to go to Titan. The Titan Dragonfly mission, really neat mission that in the works. I think they currently have a 2028 launch date is what they're shooting for in that one. That would be really cool because it's going to land on Titan and fly a helicopter around on the surface. That would be really, really neat. So yeah, that's a possibility that we might actually be able to put this idea to a test. So the promise, if you can do without the water, it's a fantastic place. You've got the energy sources. You've certainly got organic materials everywhere. It's great. If you can make life without water, this is the place to do it. So that's really what's generating a lot of the interest in this world. The problem is we have absolutely no way of knowing how biochemistry works without water. Okay, and that's a pretty harsh problem. And yes, there are biochemists who think, well, maybe we can make, there are pathways where we can make all the energy pathways work. And there are others who say, no, this is not a chance. This is not going to happen. So probably, before they come up with an agreement, I'm for sure we're going to have to go there and actually find what's actually on this world. But it's a dark horse kingdom, right? It's a big ask to say, can you have life on a completely different chemical basis than anything we know? But if you can, like I say, this is okay. So that's in our own solar system. And we can go to those worlds. So this is, in some senses, this is pretty easy. It's on the other hand, let's think about looking at all those exoplanets, those worlds around other stars. Obviously, we can't observe them nearly as closely, but we can still look for some of those global effects that we think life might have on a planet. So we're looking for biosignatures here. And in this case, we really do need to focus on the terrestrial planets in the habitable zone, in that place, in that region where water can be a liquid at the surface. And that's just really a practical problem, okay? If there's life living under the ice of a moon of a Jovian planet, we're not gonna find them. So we've really got to stick with the things we have any kind of chance, hope of observing at all. And so that's why we're looking. Those folks are mostly trying to look at the worlds where we kind of know life can work, things that look more like the Earth. These can be observed by telescope, either in a few cases, by looking directly at the stars, at the planets rather, more often by looking at when the star passes in front of the planet, when the planet passes in front of the star, how that planet affects the star's light. And I'll describe it in a little more detail here in a moment. So let's talk about some of the biosignatures we can look for in these on these exoplanets. As I said, we observe these via transit events. So this is what a transit event was. So you've got the planet passing in front of the star. We don't see this kind of resolution. It's not like we see the star as a disk and the planet moving in front. What we really measure is the light from the star gets a little bit fainter as the planet passes in front of it. But if we look really carefully, we see some of that light is passing through the planet's atmosphere. And so we can then look at that light, break it up into its colors, take a spectrum, and see if we can find what the atmosphere is made of. And we're doing this. This is not just a theoretical idea. For the last decade, there have been people actually doing that measurement. And it's been really cool to watch, because I remember back in some of the meetings like 10 or 15 years ago when people saying, I think we could do this. And now they're publishing, yeah, here's what we're finding. These are the gases these atmospheres are made of. So it's been really cool watching this. And so what we're looking for here are biosignatures in the chemistry of an atmosphere. And this is a very reasonable thing to look for, because we know that the Earth's atmosphere was wildly changed by biology. We did not start out with an oxygen atmosphere. Okay? All this oxygen around us here was produced by living organisms. Okay, that blue-green algae I showed you a little while ago. That's where the oxygen comes from. So this is the kind of thing we look for when we look at these planetary atmospheres. Are there signs of gases that we think had to be produced by living organisms? Oxygen and its byproduct ozone have long been the favorite. And of course, because we're familiar with it, we know that's an example that works. Yes, it turns out there are some ways of doing this without living organisms, so getting a bunch of oxygen in the atmosphere without a living organism. It takes some really special chemistry going to make that happen, but you could do it. Okay, so just finding oxygen by itself isn't good enough. You have to look at the chemistry of the atmosphere as a whole and see if when you mix it with everything else there, would that produce, could you produce, have oxygen remain in that atmosphere without living organisms? And there are several others that are like that too. Methane is another one that fits that description. On Earth, most of the methane is produced by living organisms. On the other hand, on a Jovian planet, methane's dead common. It's a very common. It's not. You don't need life to do that at all. And in fact, this spectrum here, and I'm not going to try to go through and explain the spectrum. But this is a sample spectrum from an exoplanet. So this is in fact the kind of thing I've been talking about, and it has methane in its atmosphere. But it's a Jovian planet. We expect methane in Jovian planet atmospheres. It's not really telling us any evidence for life, but it is telling us that yeah, we can detect this thing, this gas in the atmosphere. So that's, and, you know, nitrous oxide, I could do this list. I found, you know, a dozen different gases that were potential biosignatures in the atmosphere. But all of them have the same basic issue. You have to not just find that gas, you have to find what the rest of the atmosphere is made of too, and start trying to do the whole chemical balance to really tell whether or not that's evidence for it. So the promise, well, like I said, we know this is a thing that life will do to an atmosphere if you get enough of it. So absolutely, this is a great way to find life in on another in an exoplanet. And we know we can do these observations. The challenge, like I say, there could be non-biological ways of making the same thing happen. And so you really got to be careful about the chemistry. Okay, what about the surface of these planets? So if you can observe the surface of an exoplanet in either visible or infrared light, then you can start looking for other kinds of biosignatures. So here we look for biological processes that have very definite effects on the surface. And one good example that we see here on the Earth is something associated with photosynthesis. It turns out that when we had a spacecraft looking at the Earth, that there is a certain spectral feature, what they call the red limit, that is produced by photosynthesis on the Earth, where it turns out that things that go through photosynthesis are really strong absorbers in one energy band, and then they just don't do anything in another part of the spectrum. And you could say, yeah, well, that's because everything on the Earth is relying on chlorophyll. Would that be true, you know, with any kind of photosynthesizing thing, anything that's turning light into chemical energy? The folks who actually study this say, yeah, that they're really just the energetics of turning light into an organic compound of any kind of energy density requires that, yeah, you have certain limits that have to be met in terms of the way the kinds of light that they have to be able to absorb. So they think that that's actually a pretty solid thing to look for. So what's the promise here? Well, I mean, let's face it, if we actually saw something like this, it wouldn't just be telling us there's life there. It would be telling us something about that life. It would be telling us something about the actual underlying biological processes that they're using. So that's huge, right? Wow, we found not just life, actual photosynthesis. That would be really neat. The challenge, it's a really tough thing to do. There aren't very many planets that we have actually been able to see directly, and it's especially hard if you want to be looking so close to the star that you're seeing those planets that are down in the habitable zone. James Webb Space Telescope has just started looking at a few of those. It's a really tough observation for them. This is really pushing their limits right now. But they do have a couple of planets, a couple of things in the kind of inner solar system range that they have actually done observations. Well, they say they were actually getting actual light from the planetary surface itself. In at least one case, they were able to rule out an atmosphere entirely on one planet. So that's, I mean, we're at the beginning days of that. We may be able to see more on that. It may take the next generation on to really be able to do these observations properly. Okay, and then there's what we call a temporal biosignature, and that's really just a time. That's just saying that what if the surface is changing, especially in a seasonal way? Okay, because we know, come on, let's do this here. We know on the Earth there are things that happen in our atmosphere and on the surface of the planet that are a direct result of living organisms interacting with the seasonal changes of the planet. One example of these is something called the Keeling curve. And you may have heard of the Keeling curve. It was, in fact, the first piece of evidence that the amount of carbon dioxide in our atmosphere has been going up fairly dramatically over the last several decades. And if you look at it over year, it really is true. It's quite a dramatic change in how much CO2 is in our atmosphere. But if you look at it on a fine scale, on an annual scale, you see it also goes up and down. As there's more or less photosynthesis in the different hemispheres, changes how much CO2 there is in our atmosphere. And so that's a thing that is, and it's not a huge effect. You can see it's a few parts per million in the Earth's atmosphere. So it's not like it's an easy observation, but it is certainly a thing which is you've got to get good spectra on a planetary atmosphere and watch it at different points in its orbit. Well, that's going to be tricky if you're doing it by transit, isn't it? Because you're in transits, you always see them in the same point in the orbit. So it's probably going to have to take direct observations for that. Another one is just looking at the colors on the surface of the planet. Here on the Earth, there are large chunks of the surface that change color fairly dramatically. Not as much here in California, but there are other parts of even North America where the color of where you look at the color of the surface from space, and it's really quite dramatically different from season to season. And so that is certainly a thing you might look for on a planet. Again, you've got to have those direct observations. You've got to see it as it moves around in its orbit. So the promise, well, again, this may let us actually directly measure biological processes on the surface of the planet. Again, that'd be really neat. The challenge, we got to be really careful. I know there's a few folks here who are sort of from my generation, and I know when I was young, we would read books about Mars, and one of the things that the serious scientists back in, say, the 50s and 60s were talking about Mars was how the surface clearly was changing color brightness over the course of the Martian seasons. And there were very serious suggestions that, well, maybe what we're seeing is some kind of vegetation change that's happening as a seasonal effect. It was really dust storms. Okay, so yeah, we are wrong. And so we've got to watch that kind of thing. There's you've got to have some really clear evidence here. You don't want, because it's very easy to get fooled by other kinds of other processes going on. Okay, so that's any old life. Now let's narrow it down to just that, intelligent life, which really means, like I said, life using certain kinds of technology. What are some of those? And the first place to start, where most of our looking has been done, is looking for what I call electromagnetic signals. Okay, and that's the assumption here is that a technological civilization might well use electromagnetic signals for communication or for various other purposes. Okay, and when I say electromagnetic signals, I really mean any part of the EM spectrum. This could be radio waves, microwaves, visible light, X-rays. There's like all kinds of different possibilities. We're using a lot of these already. So, this is kind of like, okay, yeah, we have lots of experience with this. This seems like a reasonable thing to look for. And so let's see what the options. Now, of course, one possibility is that we could be looking for a deliberate signal. Somebody, either just kind of broadcasting the universe, hey, is anybody out there? Or for some reason they decided they like us and they want to they're sending something more directly to us, saying wanting to talk to us. That would be really interesting. I don't know quite know how we're going to respond to that one, but that's a possibility. That's probably not the one most of the people who are in this game would put their money on. There's some challenges to that. But leakage, okay. If I'm trying to talk to you, but I'm sending a signal that's going in all sorts of different directions, then lots of other folks can pick that signal up too. So that's another possibility. So the idea of that just kind of things that were sent out for either as broadcast or just not narrow enough beam that they, that lots of other folks get to see it. That's certainly a more likely possibility, at least. And oh, I think I left one out there. I should have had on it. Another option, which is not communication, but may actually be a much more effective one, is a radar. If you think about a radar beam, okay, this is where you send a directed electromagnetic signal, often very high energy, in a direction, and yeah, you see a little bit of that gets reflected back at you, and so the other 99% just keeps going on. It doesn't stop. These are some of the most powerful electromagnetic signals we are sending out. If you are looking for the Earth electromagnetic spectrum, this is where you'd be most likely to see it. And if somebody else has got an even more powerful radar beam and they're just kind of sweeping across their skies, that's the thing we might see long before we saw any of these other options. So, if we saw a carrier wave or radar beam or something like that, that would be an easy one. That would be like, yeah, no, those don't happen in nature. Those are really obvious. That would be, so if you found something like that, that would be a very clear signal. Not only was that life, that was a technologically using society. You just don't get any option. The problem, there are two of them. One of them is called the attenuation problem, or the 1/r² problem. And it's simply that when you get twice as far away from the transmitter, the signal drops by a factor of 4 in strength. And when you start talking about interstellar distances, at that point, the signal's dropping down to where you've lost them completely in the noise of the universe. It happens really fast. There's always hear talks about, well, maybe people on such and such a planet are watching I Love Lucy reruns now. Probably not, because I'm sorry, those broadcast signals just aren't going to be measurable at these distances. It's just not a thing. So that's one of the challenges. The other one I say is the needle in a haystack problem. When you think about this, you've got the entire electromagnetic spectrum, okay, all the different frequencies from radio waves through to X-rays that are out there. You've got all the directions in the universe where you could be looking. And you've got the time problem here, okay? You got to be looking at the right time when somebody is broadcasting. The odds of actually looking in the right direction, in the right frequency, at the right time are really small. You have to get incredibly lucky to catch that, unless these were ridiculously common. So that's the thing that sort of keeps the people who do this. They know this is like the mad money approach to saying it's like, yeah, we might make it. Of course, the odds are we won't. So that's the issue that we got there. Okay, what are some of the other things? Okay, that's what most of the search for extraterrestrial intelligence have been. But there are other things you can look for. Technological civilizations have an impact on their society, on their planets, and maybe even beyond their planet. One, of course, that we know very well is pollution. Okay, we put a whole bunch of things in our atmosphere that don't occur in nature. One that's been suggested that one might look for in another planetary atmosphere is something like chlorofluorocarbons, CFCs. Definitely, that's not a thing you're gonna get appearing appearing from natural processes in an atmosphere. But we've for a while had quite a bit of that. It's starting to go down now, fortunately. But that is certainly the kind of thing you could look for and see if that might, if you found evidence of those kinds of spectra in an atmosphere, that would be pretty suggestive that there's some kind of technological civilization. And you don't have to limit yourself to the planet too. You could certainly imagine a civilization deciding they had, say, like a bunch of, say, radioactive heavy elements that they didn't really want to have sitting around on their planet. Maybe why don't we just throw it all on the star and get rid of it, right? You put enough of that stuff in, it's going to show up in the spectrum of the star. There have been a couple of stars that people have looked at and said, the mix of metals in theirs looks a little weird. Now, the folks who do the stellar chemistry have said, after working on it for a while, said, no, we think there are ways the star could do this itself. So none of these have been that solid, but the parameter space they got to work with is pretty small. So, the amounts of, say, technetium or something like that they're seeing in these atmospheres, that star could probably do that. But if it was 10 times as much as we're seeing now, that would be a real problem if we started seeing it. So that's another thing we could look for. So we start looking at stars that have weird chemistry and see if that was see if there's something, if that might be evidence of technology. Artificial light is another one, right? You know, a lot of night sky people here. You know all about artificial light. You spent more than a few nights cursing the idea. That's right with the reader. Okay. You could actually sit down and do the calculation. Would it be possible to see the lights that on the Earth's nighttime sky from another nearby star system? And if you had something like the James Webb Telescope, the answer is no. It'd be about 1,000 times too faint. But it's only 1,000 times, right? Let's stop and think about that. Imagine you had a civilization that was, say, putting out 10 times as much light as the Earth does. That's not a wildly implausible number, is it? Right? I mean, folks have been alive as long as I have seen how much the amount of light we produce has gone up in just a few decades here. So that's not a ridiculous number by any stretch of the imagination. And imagine you had a telescope that was maybe 10 times the surface area or 10 times the diameter of the James Webb Space Telescope. Again, that's not a ridiculous thing. That's a plausible kind of thing. We're getting into that range now where you could start thinking about looking for. We're not there yet. We're probably at least another generation before we start looking for those kind of civilizations. But that's what we're talking about here. We're not talking about 1,000 years in the future. Okay, this is something, there are folks here who might be around to see that. Okay, I mentioned radar already. Propulsion systems. And yes, of course, when we think propulsion systems, we think rockets, and yes, there may be rockets could produce the light or that we would catch your interest. But I want to think about a different kind of propulsion system. A few years ago, there was a proposal that came out called Operation Starship. I don't know what's been happening with that in recent years, but the basic idea was, what if you built a solar sail with a little teeny tiny spacecraft that solar sail was carrying, and then shone a really powerful laser at that solar sail, so that it accelerates the solar sail up to about 20% of the speed of light, and then you could get to Alpha Centauri in like 20 years. So it's like. And yes, as soon as this was proposed, lots and lots of people, me included, started going through the list of reasons why that would be a really challenging thing to make work. And there are lots of reasons for that. But let's, if we're talking about civilizations that have got maybe a few thousand years into the future, they probably come up with answers for most of those problems. So if somebody were shining a laser like that, using that to propel spacecraft out of their solar system, you happen to be in the direction of that beam, you would see it. Okay, that would show up, and as a laser, it's a sort of single frequency thing. It would be really obvious that that was not just some natural phenomenon. So certainly seeing something like that would be a really clear signature again of a life of technology. So the promise. One of the nice things about a lot of these is that we could do these kind of searches as part of doing other kinds of astronomy, including looking for just general biosignatures on planets, but also just a lot of the other ways that we study other worlds, study other solar systems, or even just the way we study stars in general, might pick up some of these things. The challenges, they can be kind of ambiguous. Okay, they can be, some of them, yeah, they can really see that, you're like, okay, there's no way that could happen, naturally. But there are a lot of them where you're like, maybe not. Really hard to tell. And of course, they depend a lot on very specific technologies that would have to, these alien races would have to be using. No idea how common something like that would be. So you could spend a long time looking for this without ever finding anything. Okay, one other type of technosignature that's been kicked around for a long time is something called a megastructure. And the idea here is that a very advanced civilization, something that is maybe not even just thousands, but maybe tens or hundreds of thousands of years ahead of us, might start doing things in their solar system on a planetary or even a solar system scale. And the sort of classic example of this that was popularized by Freeman Dyson many decades ago is something called a Dyson sphere. The idea being that if you've got a civilization that civilization advanced, their requirements for energy go up and up and up, and eventually they want to start using more and more of the energy that their star produces. And so maybe the way to do that is to simply enclose the entire star in the sphere. So you can capture every photon coming off of that star and use all of that energy to power your civilization. And as a byproduct, maybe you live on the inside of it. Since then, that idea has been modified lots of different ways. There's something called the Dyson swarm that kind of does the same thing, but rather than one solid body, it does lots of smaller pieces. If you're a Larry Niven fan, remember the novel Ringworld and its various follow-ups that talked about building a great big ring around a star, and it emphasized the amount of living space you got from that, which was really quite insane. But again, these are the kind of structures you could imagine seeing from Earth. Bishop rings is another one. It's also called orbitals. These are somewhat kind of like a ring world, but a little bit smaller, more on a planetary size. But again, you get this ring, you spin it fast enough, and you can live on the inside. And this can be thousands, tens of thousands of kilometers across. These can be planetary sized objects. And if you do that, again, that's a thing we might be able to observe. So how do we see it? Well, certainly if one of these things passes in front of its star, we show up. We're already doing transit searches of nearby of other stars. So something like this would look very different than a planet would, and it would give a very distinct signature in the way it blocks the light from the planet. Another option, if you've got something like a Dyson sphere, is that all that energy that's hitting that Dyson sphere eventually has to come out. It can't just stay stuck in there, or your whole thing explodes, melts or something. So the energy still has to come out. So if we saw a star's worth of energy coming out from a place in space, but instead of it being visible light, it was all way off in the far infrared. That's what a Dyson sphere would look like. That would be really, really cool. found. So honestly, we have the technology to find this stuff now. Okay, this is not something that we're waiting on. We already know how to find these things. We got those. The challenge are the false positives. Again, is there something else doing that's blocking that star that does the same thing? We've had a couple already. There have been a couple that have been suggested might possibly be something like a Dyson swarm, for example. Turned out now it's just a debris disk. So they got better observations. So you've got to really nail down those observations, really rule out the other possibilities. Okay, so then let's get to the last major part of this. Looking for intelligent life in our solar system. And I know I'm not talking about, like in your neighborhood or something like that. But, I'm not going to go there. I will say, this was the part of this talk I was most hesitant to put in. And that's because of some basic problems that we have in the scientific community. Okay, the question we're asking here is, are we being visited, or have we ever been visited by some intelligent alien species? As I say, this is the least popular one, and the reason is simple. There are so many false positives here. Okay, we get drowned in. And so it's something where the research community really is very reluctant to dive into this, because it'd be so easy to just get lost in stuff that's completely unrelated to what's true. So what are the scientific approaches that one could do to actually look for evidence of life, of intelligent life coming to our solar system? So first thing we can do is just kind of keep an eye on what's going on around us. And honestly, we're starting to do a pretty good job of that. Okay. Right now, we have continuous monitoring of our inner solar system, looking around for objects in about the 1 kilometer size or bigger. I mean, honestly, it's pretty hard for anything bigger than about a kilometer, about 1,000 meters across, to get into the inner solar system without us finding it. There's a few orbits where you could just kind of make it work if you really worked at it, but really it's getting down to a pretty narrow window. When we start talking about things, and I'll say it worked, as I said earlier in the talk, we found 2 interstellar objects in the inner solar system. They were actually both seemingly smaller than a kilometer, okay, 200 to 500 meters. That's and just for us full-time science fiction fans, that is Starship Enterprise size we're talking about. So yeah, we're now getting to the point where things that are the sort of things that we might plausibly think of as an interstellar spacecraft are now getting hard for one of those to get in without a spot finding. That's really where we are in terms of just monitoring the inner solar system. When we come to things closer to the Earth, within say 1/10 of an astronomical unit, maybe 10 to a few tens of meters is more like the size we're talking about here. Okay, we're going to see those. Now, sometimes, yes, you hear about these close flybys of things around that size, and yeah, they just saw it because they didn't see them until they got to within a 10th of an AU or so. But that's a few tens of meters. That almost fits in the room. I don't know, but I don't think I'd want to travel between the stars and anything smaller than that. Right? That's pretty damn small for an interstellar spacecraft. So yeah, that's getting to the point where we're already looking for the kinds of things that would for that kind of thing visiting us now. So the assumption here is that these things are observed. If somehow they're sort of completely invisible to all of our technology, well, okay, yes, that's fine. But at that point, you're kind of waving your hands and talking magic. It's really hard to then say anything about what you're seeing now. What about looking at the Earth itself? Okay, are we seeing any evidence of alien visitation here from the Earth? Well, again, we have a lot of ways we're looking at the Earth, right? Weather satellites, there's all kinds of both government and private Earth observing satellites. There's like a dozen different companies that have their own Earth observing satellites that are looking at, and some of them you can buy images of the different parts of the Earth from. They'll sell them to you. And of course, there's all those spy satellites, right? They got some really cool observing technology. Did you know some of those old nuclear trees from back in the 70s, the way they monitor those is with orbiting satellites. That's one of the ways they keep track of whether or not people are actually following the rules or not. Those things are looking for a lot of the same things you'd be looking for if you were looking for a spacecraft coming approaching the Earth. And the countries involved, you know, here in the US, we tend to think of, yeah, what are we doing? Well, guess what? There are a lot of countries that have Earth observing satellites of one type or another. I mean, it's like all over the place. Okay, everybody's doing this. And then there's all the ground-based stuff, right? Your air traffic control radar, your defense radar, and then there's this one. Okay. There's these 7 billion smartphone users. You know, back in the 70s when I was growing up, you know, we were really into UFOs then, right? That was really cool. That was a thing we you know, everybody was really interested. But let's face it, you know, the best evidence for them were these, you know, sort of blurry photographs and, you know, a shaky video and yeah, right, like so what? I mean, that doesn't tell you much, but what do you expect? You know, if your camera you're carrying around is a Kodak Instamatic, and you know, maybe if you know your dad was really cool, he had a Super 8 video, but only a few of them did, then yeah, that was what it around. But let's face it, nowadays, everybody and their dog is carrying around a high resolution digital camera with video technology. And the best evidence for alien visitation coming from these are still blurry images and shaky little dots wandering around on the screen. You know, the XKCD did an interesting thing about this. The gist of it, I know it may not be as large as you'd like, is the aliens here are sort of monitoring the technology that everybody has and making sure their spacecraft are staying just out of range so that they can't get a clear picture. And it's a real challenge because everybody keeps upgrading their phones. So this is really we're in a pretty good position now to monitor signs of alien visitation here on the Earth, and we're still not getting anything really very clear. So the promise, let's face it, if they really wanted to let us know they're here, it would not be hard, right? They could make it really easy for us. And we're making it harder and harder for them to hide. So you got to start wondering whether or not this is that's a viable suggestion that they're somehow there just beyond our ability to observe. But the other challenge to looking for alien intelligence this way is that it does depend on them visiting us in a very narrow range of time. Okay, we have not really been looking for this kind of thing for terribly long, especially when you compare it to the age of the solar system. Okay, 4.5 billion years. We've only been around as a species for what, a few 100,000. That's just not very long. And so maybe we should be trying to see if we can lengthen that time frame. And so that's where looking for alien artifacts comes, right? And so here's the idea. You know, aliens come to our solar system at some point in the past, they visit, and they leave some bit of technology behind, right? You know, maybe you recognize this as the theme as the plot of 2001: A Space Odyssey. As not to mention a whole list of really bad documentaries that have come out since then. But what about nonetheless, you could look for this. You can look for, as you're exploring the solar system, you could imagine maybe you would stumble across something like this. It would be tricky, but certainly, you know, if somebody found something that really looked like it might be some bit of technology sitting on the surface of Mars, or, you know, orbiting Jupiter, or you know, anything like that, it would be I know the conspiracy theorists like to believe, well, they would have covered it up. Oh no, I know the people who do this, they'd be screaming it from the rooftops, right? Nothing would get them more immediate fame, interest than and the papers, papers and grant money, than having clear evidence of an alien technology sitting around in our solar system. So yeah, this is certainly an option. It's something, I don't think anybody's doing this now in an active way. That says, I don't think that any of the spacecraft are actively looking for alien technology here. But absolutely, if something showed up while you're studying an asteroid or something like that, yeah, they talk about it. There's some kind of anomaly like that. And it avoids the whole time zone. Okay, because hey, you've now got the whole history of the solar system where these aliens could have shown up. The challenge is, first of all, it may be really hard to actually recognize that technology from a distance. Okay, it's different than digging one up off of the surface. No, you know, actually seeing something like that from a distance may be pretty hard. So I want to finish up here then with a couple, and this kind of brings us to the one of my final thoughts about this. So the picture on the right here is a trilobite. A few 100 million years ago, that trilobite was, you know, probably among the most advanced creatures on the planet Earth. If you ask that trilobite whether or not it recognized this guy as alive, much less intelligent, it wouldn't even know what the hell you were talking about. But a few 100 million years is actually a pretty damn short time in the evolution of a planet. The odds are, if we get visited by an alien civilization, or we find evidence of an alien civilization, they're probably not going to be just a few 100 million years. It's just as likely they'll be a billion years ahead. Which means that they'll be like, well, these are some fossil stromatolites. Okay, basically algal mats, which were one of the key things on the surface of the Earth a billion years ago. That's, you know, for us to recognize that alien intelligence, to understand what the hell they're doing, is probably a lot like that algal mat trying to understand us. It could be a real challenge. So there's probably a fairly narrow window in the evolution of a species and of a civilization where we could understand them. Beyond that, I don't know that we would even recognize them. So with that, let's kind of wrap it up here. So who's going to win the race? Which of all these different ways? Well, here's my thoughts on it. I'm not going to give you the answer, but I'm going to give you where I think we are. So any of these approaches might work. Any of them might. But the two that I think have the best shot are the ones that involve looking for any life rather than life than some kind of technological civilization. First of all, our exploration of the solar system is really at this point getting to the point where we're going to start fairly soon being able to put real limits on, is there life on Mars, on Europa, Enceladus, Titan even, okay? This is now, I mean, I'm actually sort of optimistic. I may live long enough to see this, where we can actually say yes or no on some of these ones. It's really, you know, this is the things that are sort of on the books now are getting us pretty close to that. You know, sample return missions from Mars, flying through the geysers on at Enceladus. Those are all things that we could see, and they could really nail this down. And looking for biospheres in nearby planets, on nearby exosystems. Again, we're really close on this now. This is a thing where you can see, yeah, we can start, we're starting to characterize the atmospheres of exoplanets. We start to pin down what they're made of. And that's where this becomes a real possibility. I think if we can reasonably say that if we don't find any evidence of life in the next couple of decades, we have to start seriously facing the question that maybe it isn't very common, at least any kind of detectable. It's no longer, well, okay, if we don't find it this one, that's fine. That's still, you know, we haven't really explored the parameter space. We're starting to get to the point where that's not going to be true. So that's a thing to keep in mind here. The intelligent life, the assumptions in there are, there's so many, and they require knowing how an alien intelligence evolves, the technologies it uses, and we have no idea. So it's very hard to guess on. So those are much more shot in the dark type things. Maybe we'll find something. Maybe we'll go 1,000 years and not find anything. And we still may not know for sure what the story is there. So that's kind of where I am. But ask me in 2040, maybe we'll have an answer for you. And then I just want to do one last thing here, because I know I see a few familiar faces here. Folks who know, back when I worked here, we had a little baby named Annie. This club very kindly gave us a little blanket for her. In fact, that was very sweet. And so I thought you should see. Whoops, back there we go. There she is. She's now a graduate student in aircraft design at the University of Toronto, and we were at we were in Fredericksburg for the eclipse at the beginning of the week. So there she is. Thank you very much.
Q&A time.
Ooh, the scary part. Okay. Go ahead, yes.
Yeah, I thought of two challenges. One is following up what we're talking about. What if we had intelligent life on another planet where they chose to be like today? And they never went with the technology. They had other bad technologies, just nothing said in the sort of signature.
Absolutely. There are going to be lots of false negatives out there for that. Because you're right. Even you look at the history of the Earth, right? Most of our history, we were not detectable. So yeah, and there are many ways in which technology is making, like things like communication technology is actually getting quieter on the Earth rather than louder. And so you could imagine even just kind of our own technology. We may, you know, a century from now, we may not be broadcasting anything. So yes, that is absolutely, you can imagine a lot of possible technology, civilizations that we would just miss.
And also, just that if some other civilization set up something stuff, and they were in the middle of something where they had a Israel, Gaza, Iran thing going on now. And they would be gone 1,990 years, you know, we would have missed.
Absolutely, that's the time call. Okay, it's on our side, it's on their side too. We don't know how long technological civilization lasts. And, you know, the optimists say it could last millions of years, and the pessimists say you're lucky if you make a century. So that's, yes, and either one's possible.
Mr. President.
Yes.
Would a Dyson sphere moving a far infrared, would that look like a brown dwarf?
Brown dwarfs are actually, it's a little too hot. That's getting, would still be down around, that would be like a, you know, the inside surface of that sphere would still be like 1,000 K. That would be pretty, you know, you could do it, but it's not clear why.
Oh, yes.
Go ahead.
There's a pictures of it came in about the face group, but it was in classified airport stuff. That they were allowed to data mine and figured out some parameters they were allowed to see that it was there.
Is that the one that they thought hit that actually didn't go through, but actually wound up in the Indian Ocean somewhere?
Yeah.
Yeah, and even that one, there's actually a lot of debate about that one, whether it even is interstellar. It's so the estimates I've seen is, yeah, maybe 50-50. So they don't have great velocity data on that even still, and it's kind of close to the edge. You see, there's a whole bunch of things also that are sort of just barely over the velocity range where they could be considered interstellar, but they're probably not. They're probably a solar system objects that got a race to kick. So yeah, that's it. Different animal there. Anyone else? I should introduce Joanne Eisberg, my partner through all of this. She is actually, I will say, I give this talk. She teaches this stuff. This is her last semester teaching this stuff, and she's retiring. But she is, but definitely much of what you heard here today was a direct result of many years, the two of us kicking ideas back and forth, her pointing stuff out to me and I'm pointing stuff out to her, coming down on different sides of the argument at different points. So she is absolutely as responsible for this design.
Well, Dave, we'll let you hold the mic in between us. Ladies and gentlemen, I felt bad because I raided the merchandise manager's closet. And you have the official SBAU tote bag that Madam Merchandise Manager, now Treasurer as well, had. And this is our priceless porcelain cup, which has 2 mesh origins and 1 check inside for your gas. I felt bad that you only had 1 cup to drink, you know, SBAU coffee out of. You'll get here. You can share it until you get yours this fall, and then you'll have a complete set. And you did good. And thank you for coming. Next month, we're going to check out the debris around the earth and see how much of that is maybe foreign visitors. You never know. You did good, my friend. Thank you very much. Have a good, are you staying over the night here, up here? All right, welcome back. Mr. President, want to close the meeting?
Thank you. This meeting is officially closed. See you all next month.